Let us explore the third chapter of the Razavi. Basically, it deals with single stage amplifiers with different categories as common source, common drain, common gate, and then cascade. So, with the different categories of the common source amplifier where we have it in this chapter, let us start with the common source amplifier with the resistive load in this session. So, coming to the common source amplifier with the resistive load. So in this topology where we can see that the input is applied at the gate terminal, output is collected at the drain terminal, and we are making the source terminal common for both input and output. So we can justify the topology as common source. So this common source amplifier topology where it is connected with the load of RD. So this is the simple structure of the common source amplifier with a resistive load which need to be analyzed now. So while we are doing the analysis, we have to make sure, remember one thing, the same structure will be used in the differential amplifier in the chapter 4. So while we are going with the chapter 4 to make the analysis so simple, for the changes of the V input, what will be happening in our circuit in the common source amplifier where GM changes and ID changes, where it will be shown over here. So GM changes and ID changes. If you clearly understand this one, it will be very easy for us to do the analysis in the differential amplifier. So this is the note that I wanted to put in front before we start our session. So coming to the common source amplifier, yes, this is what the common source amplifier basically. So in the common source amplifier, we are trying to do the DC analysis today. Uh, Throughout the analysis with respect to variations of the V input. So V input, how will you change? V input, how you change? For the changes of the V input, what will be the ID across the device, and what will be the GM of the device? So how it is going to be affected, and how output will be affected? All the things will be exploring now. So now coming to the amplifier circuit where we can put the small signal AC equivalent circuit only under the condition the transistor when it is operated in the saturation region. So now let us elaborate how the V output change with respect to V input change. When I put that V input is on the x-axis while I'm changing, while I'm increasing from the 0 level to V input. So when I'm applying VGS over here as input, so I can say VGS is nothing but V input minus Vs. VGS is nothing but Vg minus Vs. So Vg is nothing but the voltage which you are applying at the gate terminal, that is V input. Vs is nothing but the 0. So I can say that Vgs is nothing but V input. So when V input is greater than or Vgs is greater than Vth, then only the transistor will be coming out of the cutoff. So up to this point, when you change the V input, you are increasing up to this point. Transistor M1, it will be in the M1, it will be in the cutoff. Cutoff. So when the transistor is in cutoff, when the transistor is in cutoff for the given input less than VTH, when this is cut off, this is considered as a off switch. If it is considered as off switch, nothing will flow. So VDD, whatever you apply, the same VDD will be appeared across the output. So I can say that V output will be VDD. The output will be VDD. So now when we are getting that V output equal to VDD, this is the level, right? So up to VTH, that level will be maintained constant. So now the transistor when it is off, it will be giving that output value of V output equal to VDD. The moment when you change the V input is greater than VTH, the transistor starts conducting. So it will be start entering into the saturation region from the cutoff. So the moment it is entering into the saturation, right, this is cutoff. So it is entering into the saturation region right now. When it is entering into the saturation region right now, when it starts conducting, it won't be cut off then, it starts conducting the current. So when it starts conducting the current, so whatever that VDD minus IDRD, so remaining voltage is dropped. So I can say there will be IR drop across the transistor, across the RD. So there will be ID current into RD. So VDD minus IDRD, VDD minus IDRD, this much voltage will be dropped across this one. So So now what I can say is, as the VGS increases, the drain current is also increased, because the drain current is controlled by the VGS. So VGS increases, that ID will be increased, so that VDD minus ID RT term will be reduced. So this quantity where the V output quantity will be reduced as V input you are increasing. So this is how in the saturation region V output will be dropped as the V input increased. But the problem is, when the V output is dropped, this voltage is dropped. When the V input is raised and this voltage is dropped, so this is the condition where when the drain voltage is going to the low level than VGS by VTH amount, then the transistor will go into the linear. So previously it was in the saturation region. As that output voltage is going to be fall, so when this voltage is going to fall to the level which is less than the VGS by VTH amount, then the transistor will be going into the linear. So let me put it as a equation. So I can put it as equation when the VGS is the input of something, right, minus of this one VTH, when my drain voltage, so this is the drain voltage, this is the gate voltage, so gate voltage then minus of VTH, then this one, if your VDS is less than or equal to, if it goes to that level, VDS if it goes to that level, so definitely it will be in the linear. So I can say the transistor up to now it is in the saturation. So the moment some voltage when it is applied, when VGS equal to, I consider that one as V input 1. So VGS is nothing but V input 1. So the moment when I am applying V input 1, so this is what V input 1, I am considering this one as V input 1. So that moment what happening, the V input 1 minus VTH, this point my VDS will be equal, VDS equal. So now I can say V input equal to VDS plus VTH. That voltage when you are applying, you are trying to increase that voltage so that output is going to fall. So when the output or VDS fall to that particular level, I consider that one is V input 1. So that is considered as A point. That point what happening, the transistor is going into the linear. So I can say, as that V input you are going to increase and then still increase, then still you increase, it is coming from the cutoff and going into the saturation, then it will go to the linear. So you cannot give the excess voltage of the input and you cannot give the low voltage of the input. So if you give it low voltage, it will be in the cutoff. If you give the excess voltage, it will go into the linear. So there is a sufficient base voltage, sufficient DC voltage, you have to biasing voltage, you have to give it, upon which you have to do the variations of the input. So your input should be changing from some level of the high value to the some level of the low value. It cannot be more than that or cannot be minimum of that. So then only the transistor will be operated in the saturation region, then only there will be faithful amplification will take place. Otherwise, when it is entering into the linear region or when it is entering into the cutoff region, there will be a clipping at the output you will be facing. So this is the basic functionality of the common source amplifier. So now let us draw the output waveform where we have observed up to here it is constant. It is going to fall after when it drain voltage fall by amount of A V input of this one. So then it is entering into the linear region. So when it is in linear region, it acts like a on switch. There will be on resistance of the device is on resistance of the device is 1 by mu COX W by L times of VGS minus VTH. VGS minus VTH. This is my on resistance of my transistor. So now this much on resistance, when it is offering it over here, let me draw the equivalent circuit over here. There will be RD resistance, we have it at the pull up, and there will be R on where we can observe it across the transistor. This is considered as R on. So across this one, you able to find the output. You able to find the output. So this is my VDD. So this is my transistor where you are applying the gate voltage VGS, or it is also considered as a V input. So now V output will be VDD into RD by RD by RD plus R. This is not RD as voltage divider rule. R on by R on plus R on by R on plus RD. Now this transistor where it is going to bring the output to the zero level, it will be bringing to the zero level for the value of V input. So for that what we do is we have to make sure this R on has to be becoming zero. So for making like R on equal to zero, we have to make sure this term should be zero. For that we have to give the infinity input voltage. So input voltage as it reaches to the infinity, this overall term will be becoming zero. So then only at the infinity voltage itself you will be bringing that value to the low level zero. So this is what the characteristics of the device with respect to changes of the V input. We observe the V out. Now we will be going with the rest of the things. The current which is flowing across the device and the GM of the device. So GM of the device and current across the device. The two, how it is going to be affected with respect to V input change, we have to observe now. Now now as we see the V input change from the low level to the high level, it reaches through different regions from the cutoff to saturation, then linear. It will be happening in the same way. So there up to VTH, it will be in the cutoff, and from this one, when you increase the V input from this point to A point, from this A point, right, it is going to be saturation up to here, and then it will be going to the linear. So the different equations. So as we know the current equation equal to, so there is a ID, it will be 0 in the cutoff. So in the cutoff ID equal to 0. So that is how you will be getting the curve ID equal to 0 at this level up to VTH. Now when it is entering into the saturation, as we know the current equation is ID equal to of mu COX W by L times of VGS minus VTH whole square, right? So we neglect the channel length modulation, and with this we will be getting this graph. So there is a ID which varies with respect to VGS. As we know that we discussed, right, VGS is nothing but V input. So I can replace that VGS as a V input. So V input minus VTH whole square, you got it. So this equation is nothing but y is equal to some constant terms of x minus x naught whole square. So it will be like parabola where it starts from the x naught. So this is x naught, so it starts from the x naught. So where x naught is nothing but VTH, so that my parabola starts from VTH. So now in the third region when it is moving linear, so the condition for the current is ID equal to of mu COX W by L times of VGS minus VTH 2 times of VGS minus VTH into VDS whole square. This is the current equation. And unfortunately with this current equation where VDS is nothing but my V output. So I can see that this is my VDS where across which we are taking the output. So VDS we can write it as a V output, and this also I can write it as a V output. So now VGS minus VGS is nothing but my V input. So this is my V input. V input minus VTH into V output minus V output whole square. But the problem with this equation is my ID only depends on V input itself. Then I can bring the relation ID with respect to V input. But other parameters, if it is constant, it is possible. But here it is not constant. Now V input is rising and the V output is falling. And how it's going to be affected of ID, we are unable to identify. So this equation I'm not going to consider to get the graph over here. We will be going with another graph, another equation for the ID is. So from this, what I can do is I will be putting the current equation as this is considered as on resistance because it is on resistor for the linear reason. So when it is as a on resistance, there will be VDD current will be pumping it over here. VDD voltage when it is applied, there will be ID current is VDD by VDD by the resistance, total resistance, RD plus Rn. So Rn value already you know. So let me substitute over here. VDD by RD plus Rn is some K constant. So this is considered as a K times of VGS minus VGS is nothing but your V input. So I can consider as V input minus VTH. So this is what the relation I got it. So I can say that ID is only a function of V input. This is constant, as this is constant, K is constant. VTH is also I consider this is constant. So now ID is totally depending on V input. Previous condition where ID was depending on V output, where V output is also changed. So we couldn't predict that how my curve reacts. I don't know. So this is the new equation where with which I will be identifying right the relation between the ID and the V input. So as this curve equation, I can be considered as some constant by some constant plus it is considered as like 1 by 1 plus x. X is that x axis. V input I am keeping it on x axis. ID I am keeping it on the y axis. Sorry. Here the curve equation I forgot to keep it properly. So VDD by RD plus Rn. Rn is nothing but this one. So I forgot to keep it as 1 by this one. So 1 by this one means it will be like 1 by x. It will be 1 by x. So now let me place this one in the curve equation divided by x. So this will be going like this. So if x is nothing but x minus of some constant value, if you put it, constant of around 0.2 or something, if you put it, so it will be shifted. The curve will be shifted. So from some value it will be started. So the same graph which is exponentially which are rising like this, when you can observe over here. So from the saturation from the A point, you are able to see that graph which is going to be exponentially rises. In the similar way, we will see the changes of the GM with respect to V input change, right? So as the GM conditions we put it together, GM equal to, it is in the cutoff conductance of the transistor, as we know it is 0. So you will be getting the conductance over here, it is 0 up to VTH because it is in the cutoff. So after that, as we know, the transistor will go into the saturation, so it will move into the saturation. So this is how it will be going to the saturation, right? As it in the saturation region, the condition is, if it is a saturation region, the condition is GM equal to mu COX W by L times of VGS minus VTH. So this is the simple curve. Y is equal to some constant times of x minus x naught. So there will be x naught units, right, where it intersects, and up to from that it will be rising with linearly, right? Y is equal to some mx graph we will be getting. So this is where we get that y is equal to mx plus c line, where it has intersection at the VTH. So x naught is nothing but VTH. So we will be getting a straight line which is passing to the VTH point. Now coming to the linear region, after the A point, it will enter into that, after A point, it will be entering into the linear region. So now in the linear region, let me identify the behavior of the GM with respect to the changes of the V input, as that current equation, as we know, of mu COX W by L times of 2 VGS minus VTH into VDS minus VDS whole square. This is the ID equation. So from that, GM is nothing but the derivation of that ID with respect to VGS. So if I put derivative of ID with respect to VGS, VGS, so then as I will be getting equation as mu COX W by L times of VDS. VDS I will get. Yes. So from this what I can say is mu COX W by L times of VDS. VDS is nothing but V output. Let me replace it over here. So V output. So as the GM is depending on V output, as we know that as the V input increased, so as V input increases, V out low value, it is reduced. It is going to be reduced. So GM also will be reduced. Increases, GM is also decreased. So this is how decreasing graph you will be getting it over here, right, with respect to increase of the V in. So this is how we observe the variations of the V output. So this one variations of the ID, this one variations of the ID across the device, and the variations of the GM. So I can say that this is the transistor circuit where the ID variations, V output variations, GM variations. So these three variations mostly we will be having across the circuit with respect to the changes of the V input. So this is the complete structure we have analyzed, right? So the same analysis will be repeatedly used in the differential amplifier case. So now this complete theory, let us solve it and let us explore it on the tool, and let us do the simulation now. So coming to the tool, in this session we will be dealing with the DC analysis. In the next session we will be going with the transient analysis, and for the given input voltage how it is going to be the output, and that and all we'll see. Let me select the analysis type is DC. Let me save the operating point. Let me say take the component sweep variable from uh, the input of this one, and the DC voltage that I will be changing it over here from 0 voltage to 1.8. So this is the first step where with respect to changes of the V input on the x-axis for the three variables: output variable, ID variable, GM variable. So that is the common thing on the x-axis where you wanted to do the analysis. That's what we have done it with respect to the selection of with respect to the selection of analysis type is DC. So this is the first step. So we were keeping the x-axis as the DC of the input voltage, right? So now when we are changing the DC voltage, now we will be verifying the different parameters as output. So what are the different parameters to be verified? Output is the one parameter, ID is the one parameter, and GM is the one parameter that we have to verify it, right? It from the schematic, there is a ID signal, right? This is what one signal that I wanted to verify, one graph I want with respect to V input variation. Similarly, I want another graph also. So let me choose the signal type, and the signal from output. So these two will give the graphs over here. So whatever the two graphs we are expecting, these two will be given. But the GM variable you will not find. The GM is the one operating point you wanted to find, that then directly you can get it. But problem is you want the GM with respect to different operating points, so you have to get the data. For that we discussed the procedure in the last session, as we have to go with the setup, and we have to take the simulator functions, simulator files we have to select, where the definition file over here to be selected, and as the simulation we are doing over here in this drive, in this folder, where we have to select the saved OP operating point SES file, right? So make sure in the SES file, whatever the name of the transistor we gave, the same name with which we have to do the simulation. So here in this circuit, NM naught is the transistor we are trying to do the simulation. So name of the file also name of the file in that in the file also, the name of the transistor should be nm naught. So this is what the precaution to be taken, and after that we have to save and we have to simulate once. Sorry, I didn't give the parameters over here, so it will be error. It will give the error. Amplitude is 10 milli, 10 milli. Length I'm taking it is 1 micro. D I'm keeping it as 8 kilo, and RS. In fact, we are not using RS. Let me keep it as 0. VDC around 700 millivolts, and with I'm keeping it as 10 times of the length, 10 micro. Yes, right. So let me simulate it. Yes. So V output, to some extent it will be given with the value of VDD. So after it crosses the threshold voltage, when the V input crosses the threshold voltage, from there V output is going to get, like we will be getting that falling graph, and it will be coming to the low level. So here we have to remember that low level should be right. It won't be becoming 0. So we are able to see that low level. So where we have to find one thing. Uh, so this is the minimum level where it can reach, and this is the point where it can reach to the maximum level. So maximum level and minimum level, let us find, and the same values are you getting in the simulation also, we will be verifying. So here, when you are increasing the V input, when it is coming into the linear region, so as it is in linear region, there is a on resistance, there will be a voltage of VDD into R on by RD plus R on. This is the value, right? So it can reach to this level. So it won't be becoming 0. When it is Rn equal to 0, then only it will be becoming 0. So there will be sufficient voltage, there will be enough voltage will be created across the output. So what is this voltage? That's what we will be trying to find. In the similar way, what will be the maximum current it can generate? So actually maximum current is nothing but from the VDD to the ground. So what will be the ID current? It is in the linear region it is conducted, that will be the maximum current. So in the textbook it is given like VDD by RD, but VDD by RD when the Rn equal to 0, but in the practical case Rn also will be coming to the picture. So VDD by RD plus Rn, this much current will be conducted, as already we have derived. There will be VDD by RD plus Rn current will be conducted. So now there will be maximum current, as this will be VDD by RD plus Rn, and there will be voltage of this much. So now Rn value if you able to find, then you will be getting this level and you will be getting this level both. So now let me calculate the Rn of the circuit. So now for calculating the Rn of the circuit, let me close this one and let me bring the variable Rn first, then we'll be going with the GM. So first let us go with RL results and results browser, where the DC you have to find the Rn of the device. Rn of the device. And also we'll be bringing the GM also now itself, GM also. So now let us simulate all the things at a time. Let me bring it to this. So let us find. So we'll be calculating at 1.6, let us suppose. So at 1.6 a at 1.6 at 1.6 at 1.6 at 1.62, right? 1.62, I got the R on as R on as 394 ohms. So this one is 394 ohms at V input equal to 1.62 volts. So as we know that RD, we are keeping it as 8 kilo ohms. Sorry, let me find 8 kilo ohms, and RD, it is 8 kilo ohms. So this is also 394. So VDD value is 1.8 volts. 1.8. 84 millivolts. So we are getting 84 millivolts here. We are getting 84 millivolts over here. So V output will reach to only 84 millivolts. So it can reach to 84 millivolts. So this is what we'll be trying to verify it on the tool also. So where we can take the output value at 1.62, the 84 millivolts. So theoretically what we got it and practically what we got it, both are similar. Yes, 84 on the theoretical value, 84 on the practical value, we got it. So with respect to variations of V input, with respect to variations of the V input, output, how it is going to be constant, how it is going to get how it is going to fall, and how it is going to reach to the level of 84 as per the equivalent circuit. So we able to get that, and we able to solve it through the simulation also. So now we'll find this one. So there will be maximum current it is able to pump with the value of VDD by RD plus RN. So we'll see that practically is it same or not. As that RN value we got it as this is 8 kilo ohms, and this one is 394 kilo ohms, and this is 1.8. So let me solve this one. 0.2 millivolts, milliamperes, 0.2 milliamperes. So this is the value 1.8 by 8 plus 394 that we have to calculate. Let me find it over here. 1.8 by 8 kilo ohms plus 394. If I calculate this, I will be getting of zero point 0.2 milliamperes. Zero point 0.2 milliamperes. So let me find the same thing on the simulation. So let us see that 1.62 when I'm giving 1.62 when I'm giving 1.62 1.62 I able to 1.62 I able to get that current of 214 microamperes is almost equal to zero point 0.2 milliamperes. So that's what happen. That's what we observed theoretically also. That's what we observed theoretical also, zero point 0.2 milliamperes. So with respect to the variations of the V input, where we observed the variations of the V output, in the similar way, variations of that idea also we observed. Now we'll go with the third graph, where the variations of the GM with respect to V input. Let us find. So this is the graph where already we have plotted. So where up to some extent it is in the cutoff. After that there will be rising graph, it is in the saturation. When it is in fall, when it is in the linear, when it is entering into the linear, so the graph will be fall as that as the voltage increases, as the input voltage increases, that output voltage decreases, that GM also decreases. So this is how GM graph that we'll be getting over here with respect to the variations of the V input.